here's just a few examples of circular motion and just highlighting the types of forces that are used to produce that circular motion. So example 1 is swinging a ball around on a rope. So the ball's motion, circular motion, is in that direction, so its velocity is in that direction. And if we just ignore the effects of gravity and pretend this is in a horizontal path, there is a tension force acting on that ball, and that in this case, so that's from the rope, and that in this case is providing the centripetal force that causes that ball to go around in a circle. Okay, the next example is, say we have a satellite orbiting the Earth. So there's the Earth, here's our satellite here. Looks more like a bow tie, but that's okay. It is going around the Earth in this direction. If the Earth wasn't there, it would zip off at a constant speed to the right, but the Earth is there and it's applying a force, a gravitational force, towards the centre of the Earth. So there's a force of gravity which is producing the centripetal force which is required for circular motion of that satellite around the Earth. So the third example is for a car travelling in a circle. I'm going to draw the car from above. So we're looking at it from above. Oh, it probably doesn't look much like a car, but there we go. It's travelling in a circle on a horizontal, on a flat surface, around in a circle like that. So what is it that's producing, what force is it that is the centripetal force which is producing, allowing that car to go in a circle? So think about the forces that are acting on that car. Gravity isn't producing that force. The normal force on the road isn't producing the centripetal force. It's actually friction between the tyres and the road which is producing that force. So the road is applying a frictional force to the tyres, and that's directed inwards, and that's allowing the car to go in a circle. If the road was really slippery, that car wouldn't turn, it would just zip on straight ahead, and it wouldn't, the friction wouldn't be able to act to turn it. The fourth example is of, have you ever seen one of those things where you can donate money and you put the coin in and then it spins around and around and around and around? Well, let's take kind of a cross section of that and pretend we have a coin which is rolling around. So it's actually going in a, so if we took it the other side of the motion, it would be over here, kind of going around and around like this. Okay, so what is allowing that object to go around in a circle? Just going to get rid of this one for now. Well, obviously it has an acceleration due to gravity acting on it, and that will be acting in that direction there. Now there's no component of gravity which is pointing towards the centre of the circle, so gravity can't be producing or contributing to the centripetal force. But what other force is acting on this? Well, if we just ignore friction for the moment, we know that there's a normal force acting on that coin, okay, and that normal force is from the surface of that vortex cone, if you like. Now obviously the coin is not going in a circular path which kind of goes up and around where that F value, that normal force points. So let's break it into components. We can break it into a vertical component. So that's the vertical component of that force, that normal force. And finally, we get to that horizontal component of the normal force, and that's the one in red is producing, this is providing the centripetal force which allows the coin to travel in a horizontal circle. And here's the final example. This is a loop-the-loop track, and so we might have at a couple of locations on this loop-to-loop track a cart which is travelling on the kind of the roller coaster. Could be any number of these places. We might just have a look at a few of them. Okay, and it's travelling around in a circle in this way. It's actually quite a lot of fun physics in analysing the motion of a roller coaster. First of all, I'm just going to put in the force due to gravity in all of these. So they're always going to be the same size because the mass is not changing. So these should be approximately the same size. And we always have a normal force. Down the bottom, this normal force has got to be bigger than the force due to gravity because that will give us a centripetal force, the resultant force, we'll call that the resultant force, which provides the centripetal force in order for that cart to go in a circle. Again, over here, there will be a normal force acting on from the track, and that is actually the same force that is producing that centripetal force. The force due to gravity at that position is not directed towards the center of the circle. It will be acting to slow the cart down, but it won't be producing that circular motion. Up at the top here, we might have a normal force, or in fact, you know what? Sometimes at the top of a loop, the loop like that at a roller coaster, you actually lose the normal force altogether. You have that kind of weightless feeling, you're not actually being pushed by your seat. So the force due to gravity might actually be the thing that is producing the circular motion. So we could actually just kind of draw that over there, and that would be the force due to gravity is producing that one. And over here, at this place, you have a normal force again pointing towards the center, but you also have the force due to gravity, which can be broken up into components. So I'm going to draw force due to gravity, adding something in that direction, and it also has something which is in the direction of the motion. So it's probably encouraging it to speed up, but it's also contributing somewhat to the circular motion. And I would have to add them together, and if I did that, that would be a really long, big resultant force there. So the resultant force in that central direction, which is probably not that large. But the idea is there, so there's actually a lot going on there for a roller coaster. So roller coasters, satellites, roads. Who knew physics could be so fun?